lesson where we are going to be looking at our topic which is linear motion, and your teacher is none other than teacher Ahewa William. Now when we talk about linear motion, like you hear the word linear, it comes from the word line, meaning we are talking about motion that happens in a straight line, and we know motion means movement. So you're going to be talking about how bodies move, and when they are moving in a straight line, what happens, what are the things that we talk about. Before we go any further, let's first look at the common terms that we use under this topic. We have speed. We can't do anything with something that is moving without talking about its speed. Distance, because if it is moving, it means it is covering a certain distance. We have time. Once a body is moving, it will cover a certain distance and it will be taking a certain amount of time. Then we have acceleration. We are going to see and understand what acceleration means. It basically means when the speed is increasing or decreasing. That is what we call accelerating or decelerating. We shall be looking at it in details. Then we have what we call velocity. Velocity is more of the same as speed, like you already know, but we shall see the difference. We have displacement and many others, but we shall focus on these key terms here. Now, from these key terms, we see that they are of different nature. And from your senior 1 physics, you should be able to recall that you have quantities that are majorly in two categories. You have what we call the scalar quantities and the vector quantities. Now, for this case of motion, when we say, to remind you, under scalar quantities, these are quantities which are normally, when you're talking about them, you're just looking at their size, how big they are. While under vector, we are looking at quantities which are having both size and direction. So you have to put direction into mind when you're talking about a vector quantity. Now for linear motion, which quantities are scalar quantities or scalar quantities? We have speed, we have distance, we have time. These ones you don't need to talk about their direction anyway. You just need to talk about how much is the speed. That the speed is this. What is the distance? The distance is this. What is time? Time is this. Whereas under vector quantities, we have their velocity, displacement, acceleration. So these are the quantities. This is where now the difference starts coming in. Like now you see, when we say speed, we said speed, it is just, you'll talk about its size. Whereas velocity, you have to talk about the direction, that it is moving with this speed in this direction. Whereas for speed, you just say it is moving with this speed, regardless of where it is heading. Distance, you say the distance between this point and this point is this, meters. Whereas displacement, you say the distance from this point to this point. You realize you're specializing in a direction there. So it is this meter. So they are similar because they are all measured in meters. It is all distance, but this one is a vector, whereas this one is a what? A scalar. Let's now think about this quickly. We have someone, Gerard, starts from Mbarara at 8 a.m. and reaches Ishaka town at 9 a.m. Then Musa starts from Mbarara at 9 a.m. and reaches Ishaka town at 10:30 a.m. I don't know if you can see that. Gerard started at 8, reached Ishaka at 9. Musa starts at 9 from Mbarara, reaches Ishaka at 10:30. Now, if I ask you some questions, who of these two moved faster? And how did you know? You can pause this video and you first answer those questions. Then after you play it again, you see, is what you answered clear or similar to what I'm also thinking? Now, what do you realize when you're answering those questions? You realize that you cannot talk about speed without thinking about distance and time. When you are selecting the person who was faster, when you're looking at the person who was faster, I don't know if you also agreed with me that Gerard moved faster than Musa. You realized that why did you choose Gerard? Because Gerard took only 1 hour to move from Mbarara to Ishaka, whereas Musa took 1 hour and 30 minutes to move from Mbarara to Ishaka, meaning Gerard used little time compared to Musa to cover the same distance. So you realize that when we are talking about speed, we always have to talk about time and distance, and that is exactly where the definition of speed comes from, which is defined simply as the rate of change of distance, or the distance you cover in a given time. That is your speed. You see that? Simple. Now, the moment you always hear the word rate means time. So, because whenever you talk about rate, you are talking about time. So, that's why when we are defining speed, we are talking about time and distance. So, that is definition of speed. That brings us to an equation, which is that for us to know speed, we need to get distance, we divide it with time. That's why it is rate, meaning we are dividing distance with time to get our speed. For example, if you say you have used 1 hour to move between 60 kilometers, it means you are covering every minute, because in 1 hour there is 60 minutes. So it means every minute you are covering 1 kilometer. So you have divided distance with time to get 1 kilometer per minute. But the unit we use under speed is meters per second, meaning we should always change our distance into meters and then time into what? Seconds. Correct. Now let's look at other definitions when we are talking about linear motion. We have distance itself. Like we've already said, distance is basically the space between 2 points, and its unit is meters. We have now displacement. Now this is the distance moved in a specified direction. I hope I had already talked about that. Then we have velocity, which is the rate of change of displacement. Remember, speed was the rate of change of distance. Now velocity is the rate of change of displacement. Now since speed is related with distance is a scalar quantity. So speed also remains scalar. But velocity is related with the displacement, and we see displacement is a vector quantity since it deals with the direction. So it will also become a vector quantity. Other definitions include, the velocity, it means its equation will be coming from displacement divided with time, which will still be the same unit, meters per second, since displacement is in meters. I told you displacement and distance are the same. The only difference is displacement you consider direction. If you're talking about you're moving from Kampala to Mbarara, then you now considering displacement is the distance you have moved from Kampala to Mbarara. But for a distance, I'm just saying the distance between Kampala and Mbarara. So meaning I can measure either from Mbarara to Kampala or from Kampala to Mbarara. So that is the difference between displacement. So velocity is displacement over time. Now we have certain categories of velocities or special names given to different velocities. We have what we call initial velocity, and we symbolize it with U. I've put it in these inverted quotes so that you can be able to remember that U. We shall be using it somewhere. So initial velocity is basically the velocity a body is moving with before in a given time frame I'm talking about in that case. Whereas final velocity is the velocity which a body ends with motion. So we symbolize it with V. We have also what we call average velocity, like the word says, meaning we have to take the average of the velocities. If a body is moving and its velocity is changing, then I can see the velocity at the beginning, the velocity at the end. When I add them, I divide by 2, I get the average. That is average velocity. So to put it in simple formula, it will be V. Remember, final velocity is V, initial velocity is U. So V plus U over 2 gives us average velocity. We also have what we call constant or uniform velocity, and this is what we can call the constant rate of change of displacement. In other words, the word says constant or uniform. It means my velocity is not changing. If I'm moving or I'm driving a car, the speed is not increasing, it is not decreasing. So it is remaining constant. So that's what we call constant velocity. It is important to remember that also. We shall talk about it again. So by definition, it means we're having a constant rate of change of displacement, because if every minute I was covering 1 kilometer, every minute I was covering 1 kilometer, then in the next minute I cover 2 kilometers, in the next minute I cover 4 kilometers in 1 minute, it means my speed is starting to increase. But if I was covering 1 kilometer in 1 minute, then in the next minute I cover just a half a kilometer, it means my speed has reduced. But if every minute I'm covering 1 kilometer, another minute I still cover 1 kilometer, another minute I cover 1 kilometer, it means my speed is not changing, it is remaining the same. So that's why we define it as a constant rate of change of displacement. We have also other terms like acceleration. We had talked about it. Now this is the rate of change of velocity. Rate of change of velocity, that's what we call acceleration. It means, like the word has just said, rate of change of velocity. It means for me to get acceleration, I have to get the change in velocity. I divide it with time, correct? Now, change in velocity, we already know. How do we know the change in velocity? You have to get the final velocity, you subtract off the initial velocity, that will give us the change in velocity, isn't it? So, v minus u gives us change in velocity. We divide it with time. That gives us acceleration. And the unit is meters per second squared. That is the unit. You can try it and you prove it. Since velocity is in meters per second, you are again dividing by seconds. So it should come up to meters per second squared. Now, you should take a note that, remember we said we have uniform velocity. Velocity is not changing. It means the speed I'm moving with initially is the same speed I'm moving with at the final point. So if I say initial minus final, the answer, and they are all the same, it means my answer will be 0. V minus u will be 0 if v is equal to u. So at that point, acceleration is 0. So every time you meet a scenario where the velocity or the speed is considered to be constant, don't forget that the acceleration will be 0. Now that leads us, since in these definitions we've seen some equations, it brings us to some equations of motion. That for a body which is moving, it will always follow these equations, or you can always use these equations to solve these challenges concerning this body which is in motion. And the first equation of motion is v, which is final velocity, is equal to initial velocity plus acceleration when you multiply it with time. That is the first equation of motion. The second equation of motion is S. Now, S is displacement. Don't forget, we use S, but it represents displacement or distance. It will be equal to initial velocity times time plus a half the acceleration times time squared. This is now the second equation of motion. There are 3 equations, and the third one is when you square v, which is the final velocity, it will be equal to when you square initial velocity plus 2 multiplied with acceleration and displacement or distance s. So to remind you, those unknowns, u is initial velocity, v is final velocity, a is acceleration, s is displacement, and t is the time taken. So those are the variables we use in the equations of motion. These equations of motion, they are very, very important because we use them a lot in physics, especially when we are dealing with motion, anything that is moving. Let's look at an example where we can now apply the equations of motion and what we've talked about now. We have here a scenario which says a taxi starts from rest at a traffic light and accelerates uniformly at a rate of 2 meters per second squared. Now, we've said accelerates, meaning this is acceleration, for 10 seconds and enters town B. That it started from rest, it was at a traffic, it accelerated for 10 seconds at this rate, and it entered town B. Now they want us to determine the velocity with which this taxi enters town B. We also establish the distance from the traffic light to town B, and they are telling us that if the speed limit in town B is 15 meters per second, and whoever drives above this speed is fined, was the taxi fined? That's for us now to find out. Let's take a quick look at the solution. You can pause and you try it out, then you start working on it, you play it again, and you see how we are working on it. So we need to first know what we are given in the question. One, they told us that this taxi it started from rest, meaning it was not moving at the traffic light. So its initial velocity was what? What was its speed? Good, it was 0. Initial velocity was 0 since it was at a stop. They've also given us the acceleration as 2 meters per second. They've told us the time is 10 seconds. So they want us to determine the velocity with which it enters town B, meaning in this case it will be our final velocity. We are considering that motion between traffic light and town B. So traffic light will be initial, town B will be final. Now you need to recall which equation should we use. You can now guide me. Let's first look at our equations. They are here. Now from these equations you should always see what do you have, what do you want to get, and which of these ones can work for you. Which of these equations has everything that you have plus what you want to get. When I look at equation 1, it is I need to get final velocity. So it has final velocity. Initial velocity, do I have it? Yes. Acceleration, do I have it? Yes. The time taken, do I know it? Yes. So it means equation 1 is the ideal equation to use in that part. So I will use equation 1 and I substitute in the values. I want to get V remains V. Initial velocity, we know it has been 0, plus acceleration is 2 times the time taken, which was 10 seconds. So that gives us our final velocity as what, members? As 20 meters per second. Correct. Let's look at now the second part where they want us to establish the distance between the traffic light and the town B. Still, which equation do you think we can use, members? Which equation do you think we can use? Let's look at this. These are our 3 equations. Remember, now what we have, what do we have? What do we have? We recall, we have initial velocity is 0, acceleration is 2, time was 10, and from the previous question, we have realized that it entered town B with a velocity of 20 V. So from these equations, which one can you use? Can equation 2 work? We want to get S. So S is here. Do we have U? Yes. Do we have T? Yes. Do we have A? Yes. Do we have T? Yes. Meaning equation 2 can work. How about equation 3? Do we have V? Yes. Do we have U? Yes. Do we have A? Yes. And we want to get S. So equation 3 can also work. So depending here, you can choose any of these 2 equations that you can use. Let me choose the second one. You can as well try using the third one. It should still give you the same answer. So using the second equation, when I substitute in the values, U was 0, T was 10, acceleration was 2, T was 10. So when I put them in, and it gives me this, when I simplify, 0 times 10 is 0, a half times 2 is 1, 10 squared is 100, so it is 1 times 100, which gives us 100 meters, meaning the distance between the traffic light and town B was 100 meters. And now, for part C, they were asking us that, was the taxi fined? Because they said in town, the speed limit is supposed to be 15 meters per second. Now, was the taxi fined? Do we know the distance which this taxi carried as it entered that town? Yes, it was 20 meters per second. But they are saying the limit is supposed to be 15, meaning the taxi was fined because it was moving at the speed of 20 meters per second, which was above the required 15 meters per second. That is an example that looks at equations of motion and how we can use them to deal with certain challenges. Let's have a quick look at graphs. Sometimes we can present our motion in form of graphs. These graphs have 2 categories. We have velocity time graph and we also have displacement time graph. Like you hear the word says velocity time, for them here you plot velocity against time. Whereas for displacement, you plot distance or displacement against time. Now, after you have these graphs, what they will always give you, I don't want even to talk about it much because I know it is direct. You just need to have velocities, different velocities at different times. You plot them. If when the time was 0 seconds, the velocity was 0. When the time was 10 seconds, the velocity was maybe 15. So you keep on plotting that. The same applies to distance. If the time was 0, the car had not yet moved, maybe it was at 0 meters. After maybe 10 seconds, it has moved maybe 50 meters. So you keep plotting them like that. Now, when you have those graphs, the velocity time graph, if you get its slope or gradient, it's that answer of the slope is what we call the acceleration. Because remember, for you to get slope, it means you'll be getting change in velocity over change in time. And we already know by definition of acceleration that acceleration is the rate of change of velocity, meaning you're getting velocity divided by time. So when you're getting the gradient, it is giving you acceleration. Whereas for a displacement time graph, you can guess. What does it give us? What does its slope give us or velocity? Remember, to get slope, you're getting displacement over time. That is the slope. Now, which quantity gets that? Those of you who have guessed it, you're right. It is velocity. Its slope gives us velocity or speed. Then the special thing about the velocity time graph is that if you calculate the total area that graph covers between the curve and the x-axis, it will always give you the total distance moved. That's what it will give you. So that is about the velocity time graphs. We can have a quick look at some examples. Let's look at the velocity time graph. An example is this one here. This is an example of a velocity time graph. You can look at this graph and you even describe how this body was moving. For example, I can see here we are having time, here we are having velocity. Like what I said, you're plotting velocity against time. So by looking at this graph, which is appearing like this, I can know how the body was moving. Or even when I'm given a description, I can plot this graph. For example, when the time was 0, I see the velocity was also 0, meaning the car started from rest, or the body was at rest, started from rest. Now what happened? It moved, meaning it accelerated. Why do I say accelerated? The speed is increasing. We see here this line is indicating the speed is increasing. It increased from 0 up to 20. So it accelerated for 20 seconds and it attained the velocity of 20 meters per second. If you want to even put in the value for acceleration, you can even put it there. Change in velocity, 20 minus 0, divided by time covered, which is 20 seconds. So which will be 1, meaning you can say it accelerated at a rate of 1 meter per second squared to attain a velocity of 20 meters per second after a time of 20 seconds. Then what happened when it reached there? Remember, it continued moving because we see the velocity is not 0, so meaning it is moving and the time is also moving. So it now maintained this speed because the speed is not changing. You see that the speed is not changing, so it maintained the speed for how long? From 20 seconds to reach 80 seconds. How many seconds are those? You're correct, 60. So it maintained this speed for 60 seconds. And then what happened, members? What do you see? The speed is reducing. So it means now it decelerated. Remember we said when the speed is reducing, that is deceleration. So it decelerated uniformly. You can always put in the rate if you want to put it. You now know the speed is changing from 20 to 0. And the time taken in that point is 80 to 90, that is 10. Meaning it decelerated at which rate? 20 minus 0 over 90 minus 80. 20 divided by 10. That is 2, okay? So you can say it then decelerated uniformly at a rate of negative 2 meters. Or when I use the word decelerated, I don't need to put negative. I can just say 2 meters decelerated at a rate of 2 meters per second squared and came to rest after 10 seconds, because from 80 to 90, those are 10 seconds. So that's how you can describe a velocity time graph, or how it looks like. You can always plot it. If you have given different motion, it has different parts, you can use those parts, you calculate the values like the velocities, the time, then you'll be able to plot those graphs and they'll give you a velocity time graph. You can quickly have a look at this one. This one is looking different. Now when I'm describing this one, there is something about it. Before time started being counted, the velocity was 10, meaning this vehicle or body, it was already moving by the time I was interested in it. So this is what we call now initial velocity. It means this body was moving initially with a speed of 10 meters per second. Then that is when I started counting. So it maintained this speed for 6 seconds and then decelerated uniformly and came to rest after how many seconds? From 6 to 10? 4 seconds. So that is a velocity time graph for you members. You can even look at a displacement time graph. It also looks the same. Like I told you, here we are plotting distance against time. So when the time was 0, the car was at rest. When it started moving, it covered 300 meters in 8 seconds. And then it stopped there, because when you look at this, it stopped there because the distance is not changing, meaning it was not moving. So it rested there for how long? From 8 to 24? That is 16, isn't it? For 16 seconds. So, and then it reversed, because remember this is displacement. Sorry, we used here distance, but it is supposed to be displacement. So it reversed, it changed the direction, meaning it moved back towards where it started from. Now it means for displacement, you are again reducing it. How much you are displaced from where you started from, you are now reducing it. So it changed the direction and came back to where it started after how many seconds? After 8 seconds. So that is how a displacement time graph looks like, members. I leave for you a group discussion scenario, and it goes like this. Tausi bus starts from Ishaka stage. At the same time, Global bus is setting off from Nyakabirizi, both heading to Mbarara. Tausi accelerates uniformly at a rate of 0.0125 and reaches Kabohe with a speed of 30 meters per second, while Global accelerates uniformly at a rate of 0.0112 and reaches Kabohe with a speed of 29.12 meters per second. If there is a passenger at Kabohe stage waiting to board the bus that arrives first, which bus did the passenger board? It means you need now to carry out your work, discuss it in your group, and you answer these questions. Then, what is the distance between Kabohe and Ishaka in kilometers? Remember, when you're doing your work, according to equations of motion and quantities, distance should be in meters, but here they want it in kilometers. Then, what is the distance between Kabohe and Nyakabirizi in kilometers? Okay, so alright, thank you members for sparing your time and attending this lesson. I wish you the very best of the day. Till we meet again, have a good day. Bye bye.